right, so in lesson 16, we're going to be talking about how the derivative affects the shape of a graph. We've already done quite a bit of this stuff in the past. Recall that we've said that a function is increasing if its derivative is positive, decreasing if its derivative is negative. If the function's constant, its derivative is 0. And we've applied that language to our position, velocity, and acceleration functions. We've also discussed concavity before in context. If my acceleration function is negative, we saw that the position function was concave down. If acceleration was positive, we saw that our position was concave up. And that is from our lesson 12 here. And I encourage you to go back and look at that if you want to. And we've also talked about the shape of a graph in terms of maximums and minimums. We've found maxes and mins local and global graphically. And then we've found absolute or global max and mins, extrema, using our closed interval method, which is a consequence of our extreme value theorem. But we don't have an analytic way. We only have a graphical way for finding local extrema. So in this lesson, we're going to do a few things. We're going to use our increasing and decreasing test, which we kind of already have with this information up here, but we'll use our increasing and decreasing test to talk about where in the domain a function is increasing and where it's decreasing. We're going to find local extrema using the first derivative test. We're going to find intervals of concavity using the concavity test, which you might already have an idea about given the relationship between acceleration and position. We're going to find inflection points, which are places on the graph where the curve is changing concavity. And then lastly, we're going to find local extrema another way using the second derivative tests. Both of these tests are for the exact same thing, finding local extrema. All right, so let's jump in. Right, so the increasing and decreasing test really just says if the derivative is positive, the slope of the tangent line is positive to the curve, then my curve must be increasing. I'm happy, if this is my money, I'm happy in this area over the domain negative infinity up to -2. If the slope of the tangent line is negative though, like here we've got negative slopes, my function is decreasing. And if you've got positive slopes again, just with this particular picture, we see that our function is increasing again. So all the increasing, decreasing test says is if the derivative is positive, we can just write f prime is greater than 0. Then what must be true? Then the function is increasing. So for an example with this graph, we see that this function is increasing for x values less than -2 and x values greater than +2. Example, f is increasing on what domain? -infinity up to -2, in addition 2 to infinity. A function is decreasing when its derivative is negative. So if the derivative is negative, you could just write f prime is less than 0. Then what must be true? Then this function is decreasing. Okay, so for an example, this function, make this a tiny bit smaller. This function is decreasing on -2 to 2. And I'm not including those endpoints of -2 or 2. At this moment, the function is neither increasing or decreasing. It's actually constant for a brief second right there. We're in the process of changing from increasing to decreasing. F is decreasing. Remember when you talk about qualities of a graph, like where does it have a max or min, it's saying where in the domain does this happen, or where is the function increasing, or where does the derivative exist. Those are all questions about the domain, right? So let's go ahead and do our first example here. Okay, so first we're going to use the graph to find out where the function is increasing and decreasing, and then we're going to do this problem another way analytically, as if we didn't have the picture, using my increasing and decreasing test. So first, here's my function. F of x is pictured. You can see that the derivative is negative, then it's 0 for a quick second, then it's negative again, then it's 0 for a quick second, we'll just write, how about slope? These are all negative slopes. And then the derivative is positive. Okay, so we can see that this function is increasing on what domain? I'm happy with my money past 3. Yeah? This is going on forever in this shape. So x values strictly greater than 3. And my function and here f is decreasing on what interval? Maybe I'll change my color here. Okay, so the function is decreasing. I'm not happy with my money really for x values less than 0, and then between 0 and 3. Right here, technically at 0, the slope of the tangent line is 0 there. My function's neither increasing or decreasing there. So on what interval in the domain? These two intervals put together, -infinity up to 0, in addition 0 to 3. All right, so if we have the picture, we can answer this question, but if we don't have the picture, what we're going to want to do is we're going to want to take a derivative. We're going to use the increasing decreasing test. We're going to take a derivative, find out where that derivative is either 0 or undefined. That partitions up the domain into areas where there's only one of two options left. The function is either 0 or, it's either positive or it's negative. And then where the function is positive, we can say, oh, the derivative there, I said function, sorry, where the derivative is positive, the function must be increasing. Where the derivative is negative, the function must be decreasing. Let's go ahead and do it. So step 1 to the increasing decreasing test is to go ahead and get a derivative. So here's my function f prime is 4x cubed minus 12x squared. So now I'm going to find out where the derivative is 0 or undefined. That is, I'm finding critical points, right? So f prime of x has no domain restrictions. Right? What x values make f prime equal to 0? Taking out that GCF of 4x squared times x minus 3, we get that x could be 0. We need a new color. How about green? X could be 0 or x could be 3, right? And now we're ready to do a sign test on the derivative to see where it's positive or negative. What's happening here, right? When you put an input, a number into a function, and in this case it's f prime, but any function for that matter, when you put a number in, there's only 4 options. Either you get DNE, right? There's a domain restriction, or you would get 0, or you'd get out a number, and the number has only 2 choices. Either that number is positive or that number is negative. Not enough colors for Lindsay. All right, so that's what we mean by saying finding the places where the derivative is 0 are undefined, in this case at x equals 0, and at x equals 3, we've now partitioned the domain into these 3 zones: numbers less than 0, numbers between 0 and 3, and numbers greater than 3. And so there's only one of 2 options. I put an x value in to my function, and it's going to spit out a number that's either going to be positive or negative, and that's it, right? So here are these intervals. X values less than 0, which we see right there. X values between 0 and 3. And x values greater than 3. That's it. So all I have to do is pick a number less than 0, any number, and stick it into f prime. And you could stick it into f prime right here, or f prime in factored form, doesn't matter. And all I want to know is that number positive or negative? You know, so how about something less than 0, minus 1,000. Minus 1,000 squared will be positive, times 4 is positive. And minus 1,000 minus 3 is negative. A positive times a negative is negative. So since the first derivative is negative, I know that my function must be decreasing. You can pick any number. And I could pick minus 1. Maybe you don't like plugging it in factored form. Put minus 1 in here. Minus 1 cubed is minus 1 times 4 is minus 4. Minus 1 squared is positive 1 times 12. So we've got minus 4 minus 12 is negative, right? So just pick any number less than 0, plug it into f prime, we'll get out a negative number. Now pick a number between 0 and 3, you know, like x is 1. 1 squared is positive times 4 is positive. 1 minus 3 is negative. Again, we've got a positive times a negative. Negative. I know my function is decreasing. You could go ahead and get specific function values, but one thing that's nice about looking at it in factored form, I don't care what the number is, I just care if it's positive or negative, and I can kind of do that arithmetic in my head faster. But you could just pick a number, pick 1, actually go find f prime of 1, and go, oh my goodness, that number is negative. Now pick a number bigger than 3. 10. 10 squared is positive times 4 is positive. 10 minus 3 is positive. A positive times a positive is positive. I know that my function is increasing. Okay, and then step 4 is to just really interpret these results. So I get to say that my function is decreasing on what intervals? These two. And my function is increasing on what interval? This one. So we'll just write that there. F, maybe we even name it. It was x to the 4th. Boom. Is decreasing on what intervals? Minus infinity to 0 and 0 to 3. And it's increasing on 3 to infinity. Right? And notice these are the exact same as what we have up here. Check. Okay, so that is our increasing and decreasing test.